Hello, everyone. So, in continuation of the interview series regarding deep learning, it has been quite some time since I posted new videos regarding deep learning and general interview process. So, in terms of the second round details and the further round details way back for Adobe in the deep learning phase. So the second to the ultimate rounds, that is 3 successive rounds together, were mainly concentrated on deep diving on different deep learning concepts. So some of the questions which were asked falls into certain categories. And in that case, one of the most important things that happens is just share the screen. Right. So generally for the deep learning interviews, right? So a few things happen, right? So 2 to 4. So a few things happen. So the first, so the few questions get asked on questions on sampling theory. So these include some questions like, so let's say a product on Amazon has mixed reviews, right? So these reviews are in the form of, let's say, 4 people have given a rating of 3.5, and let's say, for example, 6 people have given a rating of let's say 4, right? So what can we say about, so the question is, how can we predict the probability of this product being bought by next 10 customers? Okay. So these kinds of questions on sampling generally gets asked. These are very preliminary questions based on rudimentary statistics and probability theory. So basically, if you know, it is a very simple problem where you have, let's say, a distribution xi with a mean rating of yi, then it is nothing but summation of let's say xi multiplied by yi divided by summation of the total samples set, right? So this will give you an average rating of your entire sample. And in most of the cases, average does tend to give a good forecast of what is going to be in the next, let's say, 10 or 100 samples. So if you increase this value, so the next question which the interviewer might ask, that if you increase this sample of 4 people to 400 people, and let's say 6 people to 600 people, then can we predict for the next 10 people? Then it becomes a sampling problem, where you are estimating the values, where you go on increasing the values of your variables, that is xi, right? And this in turn increases the weightage of each of those factors, right? So, but the basic idea behind on this is basically the same, because it always sticks to the median value of your statistical distribution. So the questions, second kind of questions which get asked are basics of activations, activation functions, nonlinearity. So let's say linearity, and some deep learning concepts regarding convolution stuff. What are the deep learning algorithms being used? So DL algorithms, let's say convolutions, and the mechanism of convolutions, how they happen mathematically, right? So one of the questions which gets asked is that is nonlinearity always needed for an activation function, right? So very basic and rudimentary question, the conceptual question. So if is nonlinearity needed for an activation function in the case of any kind of deep learning models, right? Which basically implies you are using a nonlinear backend for this. So let's say TensorFlow or PyTorch or Sonnet or any kind of deep learning framework which does this kinds of nonlinear algorithm optimization. So if that is so, if the answer is yes, then can we say the same for a simple function, linear function like, let's say, ReLU, right? We know that ReLU is kind of a simple regularized linear unit, right? Simple function, right? And can we say that it is the same? Now, when we try to answer these questions, always try to say that always try to specify the range or the domain of the function that you are trying to explain your nonlinearity. This is very rudimentary to calculus. So let's say for any function f of x, right? When you are specifying, let's say, a continuity, right, or differentiability aspect, differentiability ensures continuity around a certain aspect in the vicinity in real functions. So if you are telling that, so you should be knowing that, you know, we should be specifying in which range your function is assumed to be continuously differentiable. So range of the function under which it is continuously differentiable, right? Okay. So some other questions gets asked, right? What do you mean by different? What are the different types of? What are the different steps which happens in the case of convolution networks? So the steps happening inside convolutions, right? So what do we mean by convolutions, right? So that is one important question which gets asked. And how does changing the filter size, right, you know, kind of affect the way the convolution filters or optimizes, or I would say rather optimizes your image distribution, right, to better classify, segment, or do any downstream image kind of tasks. How does that happen? So in anything related to convolutions, always try to understand the mathematical significance of convolution, right? So when you tend to lower down the filters, always try to remember certain formulae which is there, which governs the output dimensions with respect to the input dimensions. Provided you have an n cross m, right, input image with an let's say I cross j filter, right? How does the dimensions of the output image correspond to that input image and the filter combined with certain other parameters called as padding or strides, right? There are dedicated formulas, linear formulas, right? So you subtract the stride, add the padding variable, right? And then you divide by the entire filter length, right? The dimensions of the filter. So these kinds of simple equations are very important to understand. Some tricky questions might appear that you are given an input size. Let's say a question which may come in is like, we're given an input dimension of images, right? Let's say n cross m, right? And the filter dimension of, you know, I'm assuming a rectangular filter, right? Not necessarily a square filter. And let's say stride is S, and you know, padding, we are applying, let's say padding is optional, but we are still applying a padding kind of P, zero padding, right? So what is the dimension of the output? Dimension of the output. So these are direct formulas to perform that, right? And some of the important questions might come in is what is batch normalization? How is it different from layer normalization? So when normalization comes into the picture, we have to always remember that it is related to the mean and the standard deviation of your distribution. In your case, the data set variance, right? So batch normalization is something which is done, at a mini batch level, right? So whenever you pass in your training data set to your loader, which automatically does this, modulates your mean and your standard deviation of your data set to better cater to your language, to your learning model. Layer normalization is a little bit separate. Layer normalization is something that you generally see in some architectures called as transformers, right? Where you are trying to optimize, you're trying to find the distribution of your sample of your layer that is containing all the data sets, right? It not only includes the weights of your layers, but also the parameters which is getting invoked there. So this is a very trivial questions which gets asked, and also try to look up about these terms, whitening and all. What is whitening? It is nothing but taking the mean and the standard deviation of your variance data set. Yeah, after this, there are generally some questions which was asked on optimizers. So what kind of optimizers are there? What is adaptive momentum? Why we need momentum-based optimizers? What are the new variants of momentum-based optimizers and these kinds of stuff, right? So these are the basics of DL, right? And of course, there are a lot in other interviews. People ask a lot of questions on these aspects. Transformers, what is the architecture of transformers? What does a transformer do? What is meant by self-attention, right? What is the significance, mathematical significance of self-attention? It's a very common question which gets asked. Of self-attention, right? Always remember that when we are trying to do any kind of attention mechanism, it is nothing but trying to figure out correlations between certain entities of the distribution. So we'll be looking into how we can do a code level implementation of these kinds of stuff, right? So these are just the theoretical and kind of mathematical logic questions which gets asked before some questions on how to on a specific topic. So let's say if we move to some level 3, right? So in level 3, what happens? This is, by the way, for level 2, right? Very basic kind of level, but very important and very the follow-up questions are something to be kept track of, because as the questions increase, you go deeper into the concepts and it becomes really challenging, right? So level 3 is nothing but a case study. So let's say at the time of interview, I remember that the question that was asked about Adobe was trying to figure out templates and generate templates. Given an input template. So let's say you want to generate a birthday template, right? You want to generate a birthday template, okay? So how are you going to generate different kinds of birthday templates in the PDF format from your input samples? Your input may or may not have birthday templates, right? So how will you apply your deep learning model, right, to do that? Okay, and this is one of the questions, one of the case studies which got asked. And whenever this kind of question gets asked, there are various aspects of this. So how to tackle these questions, because you have to ultimately write a pseudocode to just grill them the different aspects of it. So first target, when you ask about the input specifications. So input specifications generally includes that whether we are only going to restrict ourselves to RGB based image samples, which can be handled by general frameworks. So this basically includes asking more trivial questions or more deep down questions, right? Is it going to be in NCHW format or NCHW format, right? Channels last or channels first? Channels last is generally the one which gets followed in most of the cases, but yeah, so these are certain questions which gets asked, right? And how do we want to generate the samples based upon your given input, right? So let's say you have a template on your screen, right? Take that template to generate a new template. So decide upon the general architecture of the model, right? But even before we go to this stage, we have to understand the algo, what we are going to write, right? So the algorithm is going to be able to generate new samples based upon the given input samples, right? So some form of generative learning is going to be there, right? Some form of generative learning is going to be there. But here the input distribution is in the form of images, but not so straightforward, because you are going to abstract certain parts of the images and you are going to take some parts and put it into some other images. So basically this boils down to something called a segmentation, right? Identifying certain blocks and trying to reproduce some variants of those blocks in the new images, right? And the second thing is that how are you going to, so you have decided upon the algorithm paradigm that you are going to take up, that is segmentation. And also you have to take up, since the another important thing is the input may or may not have the same specifications as that of the output, right? We're generating something. So you might think that, we can have two different kinds of things in this case. That, of course, this is generative learning, you are going to need a GAN architecture, right? So this GAN architecture is something which you need, that is rudimentary. And you need the GAN to kind of take input image samples and apply the weights parameters and transfer them to the new samples. So you need some variants of transfer learning, some flavor of transfer learning inside this, right? And you are going to perform some segmentation to identify certain blocks, and you want to generate new blocks from that. And yeah, and you have to finally work on how you're going to optimize the loss, right? What is going to be the loss function of your model, right? So these are the different aspects as a preliminary before scaling up or scaling out, right? Just a simpler model, right? What we are going to tackle, what paradigms we are going to follow. Now that we have understood that it is a GAN that needs to be done, right? So one of the important aspects is what kind of GAN do you want to be, right? So let's say this GAN, the GAN can have many flavors, right? So what GAN do we think is kind of interesting in this case is what are the possibilities that we have in the case of GAN? So we have a simple DCGAN, right? Let's say we have a DCGAN, right? What does a DCGAN do? DCGAN is pretty trivially simple, right? It does not, you will have certain convolution blocks. It tries to encode the entire input image into a block, and it tries to, it has two different blocks, right? Generator and the discriminator, and it tries to produce some outputs, right? So in this case, a simple DCGAN might not do the trick for us, but we can definitely try. So here, as a first step, we are going to start off with a DCGAN, a very simplistic GAN, and we try to see whether we can apply the segmentation logic on it, right? We try to see whether we can apply the segmentation logic on it, and then we try to assume that we can whether we can be able to build this kind of loss function, which will be better able to detect and generate new samples. So in this case, just 1 second, let me just show this. Okay. So in this case, we can start off with the DCGAN, but it might not be able to give you a proper solution. So whenever we write a GAN, right? So if someone asks you to write some pseudocode backend as something like this, right? You have to always remember that when you are trying to idealize this kinds of concepts, the main thing is to identify, write up blocks of the neural network separately. Okay, so here you are going to write a DCGAN. We will start off with a DCGAN to solve this issue and see what challenges we face in the subsequent steps. So what does a DCGAN contain? DCGAN contains a simple generator block, right? Sorry, it is going to contain a simple generator block, right? And it is going to contain a simple discriminator block, and it is going to contain a convergent loss function, which is generally, let's say, go with the simplest cross entropy loss function, right? Now, even before writing this, can we guess like what we are going to come up with some problems? Let's say we are feeding the entire birthday template as an image into my DCGAN. So so the first question, which I did not tackle over here, is which should be asked is for the input specifications, right? 1.1, I'm writing it as the modalities, right? The modalities means that whether the template is going to contain texts and images together, or only images or text alone at one time. So for simplicity purposes, we are going to assume that it contains only images, that no text, right? So if it contains simple images, right, then this DCGAN will kind of do a good, I would say, a more stable result than having multi-modalities, because in that case it will just do nothing, right? But DCGAN is kind of a, so if you are writing this, so it should be something like, right? So what is your generator going to contain? So your generator is going to contain certain, so let's say you are writing certain, self, right? What is it going to contain? Some filters, strides. So always remember, for a DCGAN, what the architecture flow for the generator and the discriminator are more or less similar. You are going to have convolution blocks and deconvolution blocks, followed by batch normalization and preludes, right? So the flow is generally like something like conf 2ds, followed by batch norms, and that is where the previous rounds or the conceptual understanding behind batch norms becomes important. Is why we need batch norms in the case of convolutions. Because if we do not give batch norms, you will see that the distribution of the input samples after you apply the filter of the convolution might not be properly addressed as you go down the convolution pipe, or as you go down the generator pipe, right? So because the mean and because whenever we apply a filter of a convolution on an image, the interesting thing that happens is the variance between the RGB values of your filters in the median level. That means your mean and standard deviation. That is why it is interesting to understand this. And leaky ReLU, right? So leaky ReLU is a kind of a ReLU function, same as the ReLU function. For the positive side, it is nothing but y is equal to x, right? 45 degrees angle in the positive x-axis, positive x or positive axis, first quadrant. But for the negative side, for x less than 0, it is not always 0. So it degrades, right? It degrades with a value less than 0 in the y-axis, right? So leaky ReLU is something which is sometimes needed to flush out any kind of bias that is getting induced due to any kind of operations or kernel initializations by any kind of layers, right? So these are questions which might get asked, right? So you have to follow up on them. So you can just write something like, these are just pseudocode, by the way. So assume any kind of filters. So there must be, in some some parameters we want to add. So self dot, if you want to add certain things like, let's say, batch norm, EF keras. Want to give some arguments over here, right? and self dot activations. So you want to have something called as leaky value, right? And in certain cases, you want to have something called as in some cases you do have certain dropouts, right? But those are experimental mainly for discriminators. You generally want to put a dropout. So in that case, that is important, right? Now, whenever you write a kind of a wrap inside your entire module, right, inside TensorFlow layers, right, you basically would like to have your init method, right, where you initialize your different modules that you're getting called, that you're calling, right, and the forward module, which is just for the forward pass, and the backward pass will be done by the TensorFlow. This is the TensorFlow backend, so it will be done by your TF gradient tape. So your gradient tape will be responsible for doing all kinds of back propagation and everything, right? So when you have a forward, right, you are going to pass in the input images. Now, input, this input images is not going to be entirely input images. It is going to be, of course, adjusted or augmented images. So augmented images, I'm just writing it as like this. I mean, hashtag. Okay, so you are going to have something like TF image, left to right, flip left to right, flip function, right? If you want to flip them, or what else? If you want to resize them, TF image dot resize, right, or reshape, whatever, right? I think the function is resize though, and you can add any kind of any kind of augmentations on the images, right? Now, so now it becomes pretty much straightforward, right? So you want to have self.conf1 input images, right? And you are going to get the output X. Now this is very simple. Now you have to just write in the layers. You have to write in the layers one after the other. Now you have to understand what this layer does and why are we plugging it one at a time. So let's say it's one, right? And you just go on do this like bash norm. After that, it is leaky redo, right? Self.activation. Let's say you want to put in x1, right? And you give x2, and you do this multiple times, right? So I'm writing it as keep doing it multiple times, right? And you generally get to see different kinds of as you increase the number of blocks inside this, the more interesting it is going to be. Okay, but always remember that we cannot keep on increasing them over and over again, right? There has to be a limit of this. In some cases, in the DCGAN, we also have something called as deconvolution networks, or the better known term is called as in TensorFlow it is called as conf transpose or conf2 d transpose. Okay, the reason why deconvolution is there, so self.deconvolution is let's write as df here as layers conf to the conf to the transpose, right? So this conf to the transpose is nothing but it tries to from your convoluted output image, it tries to deconvolute, right? Deconvolution is done by an attempt to try to reconstruct the samples of your input image from your output image, right? By using the weights, by using the parameters that has already been added to the output image through the convolution operation. Okay, so you use the convolution operation to transfer the weights of your parameters to your input images, right? And then you try to deconvolute back to get the input image. So these are just some important tricks. Here it is similar to something called as reconstruction. And the general equation is for every pixel, you subtract the deconvoluted values of that pixel. So for example, so let's say for every pixel ij, so conv ij denotes the convolution value of that value of that pixel minus the the original value original, that is the original input value of that image of the pixel ij whole square, right? So this is the simple equation, effective equation of your deconvolution, and you generally try to perform a log loss on it, right? But this is the general idea. So this deconvolution block is also going to contain, your self.deconv x2, x3, right? And you go on writing this. Sorry. You go on writing this, and this continues for most of the cases, right? And you are going to design a loss function. So the loss is going to be very simple. It is going to be a TF keras. What is that? I mean, a cross entropy. Sorry, yes, keras cross entropy. Seeing categorical cross entropy will also work, but I'm assuming. So categorical cross entropy will also kind of work in this case, right? So TF keras loss, we're going to, in the case of the generator, always remember that you're going to get, always remember, right, for the generator, you are going to have a CE loss of fake outputs given fake inputs, right? So fake outputs given fake inputs. These fake images are going to be sent from the original input samples. The discriminator will try to generate them. They try to discriminate them, and the generator will generate the fake outputs to confuse the discriminator. So I'm just writing it as fake outputs, but you can just put this x3 over there, or whatever output is going to be input images. But always remember that this is going to be fake outputs, fake inputs. Okay. And you return that loss function. Okay. Now same architecture kinds of goes for the discriminator. Layer, right? And you give a same architecture. I'm writing it as same architecture as the generator module, right? For the discriminator, the only difference lies in how we write the forward and the loss. So the forward is also going to contain the same layers and the same flow of the layers. The difference lies in how we design the loss. Now for the discriminator loss, it is important to remember that the discriminator loss is going to take the original input samples, right? And it is going to, the loss function of the discriminator is going to be real loss and the fake loss together, like coupled together or added together, concatenated together. The reason why is that you have to remember for a discriminator, the task is to always detect fake images coming from the generator, right? So basically the entropy function is best suited for this is binary cross entropy, because it has to detect whether it is true or false, correct image or fake image. The generator has a lot of possibilities. It can try to produce n number of images from its input sample distribution. That's fake loss. Okay. So real loss is going to be. So I'm writing it as categorical cross entropy, just for simplicity, right? Your real loss is going to be the real images. That is your. I'm writing it as real output, real images. And your fake loss is going to contain your fake output and your fake images. Generally, this fake loss comes from your generator module, because they are the ones producing the fake images. Okay. Now, what you do after this? Return real loss plus fake loss. Okay. So basically, this is the idea behind your generator discriminator. Now, this is the same for any kind of discriminator that you write, right? Not specifically for DCGAN. Any kind of GAN architectures is bound to have this kind of flow or rudimentary flow in the case of your discriminator. Okay. So now that we have this entire generator and the discriminator blocks, we can combine them together to give a combined loss. Now, not a combined loss. Now, let's say we write a GAN, DCGAN. Okay, so we combine them. So how do we combine them? Very simple. We have done most of the work in this case. We are going to have generator equal to generator class. with the input images, right? Discriminator with the images, right? Now for writing the effective flow, we generally write with this. If you are using group TensorFlow, we write something like this. As generator, right? For the generator scope, right? And tf dot gradient tape for the discriminator, right? As discriminator, because we are going to have two gradient tapes, because we are simultaneously going to train the generator and the discriminator at the same time. Okay, so you are going to get the loss of your generator loss, which is invoked from the generator class. You are going to get the discriminator loss. I'm writing it as disk loss from the discriminator class. I mean, right? These are not classes; these are just instances. But anyway, yeah. So now that we have, now we can, what we can do is we can feed it to the gradient tape, right? So you can just parse these values inside this. So you can have, let's say, tf dot effective. Let's say you are going to have an Adam optimizer, right? Let's say tf optimizers dot Adam, right? And you are going to pass in your different losses for your. Actually, you write two different optimizers for two different cases, but here for simplicity, for each gradient tape iteration, we are going to take the losses and we are going to feed it into the optimizers for the next step, right? So this ensures that this forward is getting called for both of these blocks, right? So this forward is getting called for both of these blocks, and you are going to have, you are calling the gradient tape and then you are calling the optimizers. Okay. So basically, that is the pseudocode when you want to write. Of course, there are syntactical errors in this, but the general flow, it will be very much easier to communicate to the interviewer to this. Now, this becomes very complicated when you write transformers, when you try to implement pseudocode for transformers, which will be coming to in the next few sessions, right? Now we have implemented a kind of a pseudocode architecture for a basic DCGAN, which feeds in the input of one modality. That means only input images, the templates, right? If we go back to the question, right? We have now implemented the DCGAN, Now you feed in the model. Now feed in input images after augmentation, right? Now, now your criteria that it is able to generate only image based, kind of, let's say, samples as output. As outputs, that will be clarified. That will be assumed. That will be done, kind of. But the samples that you're getting in the output is not going to be that much efficient, because DCGANs are good, but there are way more better architectures, which kinds of plugs it in. We have just used a simple convolution block. So the interviewer might ask you how you can improve that DCGAN. So you can say that instead of the convolution blocks, simple convolution deconv blocks, you can have let's say residual blocks. You can have inception exception blocks, pure convolution based modification. Inception exception, these are neural network architectures for vision, primarily having residual blocks and the best suited will be to have bottleneck ResNets or residual networks, bottleneck residual networks, which try to transfer the images or try to transfer your parameters and your model weights, right, across your different layers and obviously having some residual blocks so that you bypass the layers just to reduce the number of parameters during training stage, right? So as to not suffer from bottlenecking or very kind of gradient becoming very slow or something like that. So these are certain things we can improve for the DCGAN. So the interviewer might ask, so what else can we try other than DCGAN? Now, considering this is only for a single modality that is only for images. Given an input birthday image template, right? We are trying to sample or generate new birthday image templates, only images, nothing else. So birthday image template is going to have only, let's say, balloons and everything, balloons and cakes. So let's say based upon our image network, we are going to generate something, let's say balloons, cakes, and toys, and something like that, right? Now, what else can we do better in this case? So the next question comes in, what else can we try? So the next things which comes into this is, how about instead of directly applying convolution, applying GAN on the entire input image, we segment parts of the image and then apply small GANs on the individual samples. So this means that, let's say we have an image of a cake inside. We have an image of a cake inside the central image, right? We segment that image of a cake and we try to generate new possibilities or new images of that cake. And we do this for every individual entity that we see inside that particular image. It can be balloons, it can be toys, it can be small children, it can be anything, right? Because it is a birthday template that we want to do, right? So that can also be done. There are certain architectures for this, which is there. One of the most popular and famous being kind of called as UNet architecture, which is an encoder and a decoder kind of a dual architecture for your image for GANs. And if you want to perform segmentations on units, you need to have some additional parameters called as pixel GANs, or better known as I think pix to pix. So these are certain other architectures which you can apply to pix to pix. Now, based upon, in my case, what I had to do is, I had to explain how pix to pix also works and the pseudocode for that using UNet architecture, writing the pseudocode just like we did for the DCGAN, and to see how the effective change in the loss functions try to give us an advantage. Okay, so this is. So in the next, since this video is quite some long, right? In the next, we will be seeing how to build a pseudocode for the pix to pix and what other questions gets followed, right? So basically, after this, the next question comes in is, we have lots of different image kind of generators now, right? We have very complex, based upon the UNet architecture only, we have diffusion-based image architectures. But at that time, diffusion was not that mainstream, right? So at that time, during the interview, I was asked about, what if we change the modalities? What if we have different modalities, right? So you are going to have textual data as well, plus image data. So here is a clear-cut case of your segmentation. You have to segment the input images and your textual data. For the textual data, you need to sample the textual data because you are going to apply kind of generative learning on your textual data as well. And you are going to apply generative learning on your image data as well. So this problem becomes a little more complicated. Okay. And in that case, what is important is, how do we, so let's say you have two different samples of your textual image corpuses, right? And how do we maintain the integrity of your generated input image text, input of your output template? The integrity means that birthday image template should resemble a birthday image template. It should not resemble, a CV template or something like that, or a resume template or that, right? So this integrity is very much important. So when you have this integrity, right, whenever you have these kinds of integrity kind of related questions, right, you are going to generally have something called as a two distributions, and you want to try to maintain the distance, effective distance, or by distance I mean the distance between the distributions as low as possible. So this basically implies that you are trying to perform some divergence tests on it, right? How divergent are one point in a statistical distribution different from other point in a distribution? Okay. So you might have heard about KL divergence, one of the most popular divergence algorithms used in the case of loss functions. That is what I had said during my interviews at that time, right? So which is by default one of the standard methods being used everywhere in the industry. So we will follow up on these kinds of questions, case related questions, and we will go to level 4, which was the final the final round, which was a little bit more complicated when we had to try in different transformer architectures as well for the textual index. Following this, so Adobe generally has a way for particularly to use these kinds of case studies in the previous session to continue on that case study and to understand go more deep in depth into the architecture for deep learning, right? So I hope you learned something from it, how the interview flow works. Not only that, the intricacies of different kind of architectures, when we need them, how to understand them from a given question, business topic, right? And I hope to see you in the next video.